What was it? Okay, so as a reminder, what was it? In general, what was the quest? What was the setup? When you look at the handout, it starts with single period, perishable product model or something like that, doesn't it? So the situation is, you've got one product, and you have a limited time in which you want to sell it. You don't know the demand because it's stochastic. The demand is random. It's a random variable. And you know its distribution. You're assuming that you know the distribution of the demand in that period in which you have to sell it. Okay. And there are three costs. One cost is of buying one unit of the thing that you're selling. That's the C. You see that's the C. And there's a cost of running out, so being short of one unit at the end of that period. That's this P. And there's a cost of H, which is the cost you have when you are left with something that you don't manage to sell. Okay? And the question is, how much to order before that period? And you kind of think of it as you can't reorder if you run out. Okay. How much should you order? And that's this S, the decision variable. How much should you order to minimize the expected cost? Okay. It's expected, we don't know how much it's going to be, but we can calculate based on how much the demand is going to be as a random variable. Okay. So the cost was there, which was a sum, because we were assuming that the demand was a discrete distribution, so our values 0, 1, 2, 3, 4. But we can approximate it with, especially if there are large numbers of these things that you're selling. Number of copies of a newspaper could be about 100 or something, and that's the typical situation. It's why it's called a newsboy model sometimes. You need to order a certain number of newspapers. You don't know how many you're going to sell on that particular day. Well, you can't reorder, or if you reorder, there's a high cost related to it because you go somewhere and get it from another news agent or something. And if you're left with them, then there's a cost of, well, maybe eligible cost, but you have to get rid of them, or maybe you can sell them for a little bit, like the newspaper, and then the stage would be negative. So this was the example that we had with the bicycles. It's actually negative. See in a minute. Okay, so the costs are the three. How much you pay for the stuff is simple. How much you pay. This is the mean number, expected number of things that you will be left over with after that period, if the demand is less than the number of things that you buy. And if demand is larger than how many you ordered, then you get this cost, and this is its expected. What we wanted to do with this, minimizing this, was differentiate it by S. S is the decision variable, that's the unknown. And we differentiated this integral in this way, and what we got was, well, we did it like that, using what's called the fundamental theorem of calculus. So the fundamental theorem of calculus says that if you have an integral like this, from 0 to S, then its derivative by s is that function inside in s. So this gives you s times fs. That's this bit here. And we used it here, and we got fs, and s was before the integral. For this one, we differentiated as a product of two functions, so we got this. Now, these cancel. And this is what's left over as the derivative of that term. Now, if you do a similar trick with this term, what you're going to get is this. And CS is just a constant times variable, so the derivative is the constant. So now this is what the derivative of the cost is. Okay. This formula that I promise you. I think I got a sign wrong somewhere there when I wrote it first, but then I corrected it before putting it online. So check that you have the same thing. Oh, I've deleted something here.
What was that called? The fundamental rule of calculus?
So the fundamental theorem of calculus is something you did in year 1 with Killian, which says that if you have the integral of any function from anywhere to s, and you're differentiating it by s, there's no s in there, then what you get is the function that's sitting inside in s.
And for all examples of this, would we have to apply the fundamental theorem of calculus?
Well, if someone told you to do this, then yeah. It's kind of, think of, well, it's an easy theorem. I think I said, well, easy. Yeah. It's relatively easy. When you think of the physical interpretation, so this is the speed based on time, x is time, this is the speed of something. And then you can do the integral from time 0 to a certain time, and you get the distance that something has traveled. And when you're differentiating the distance, and again you get the speed back. So that's the general idea. Okay, so what you get is this. Now, we've done that thing in detail. This you can check yourselves. And this is equal C plus H times F S. Okay, so what's F? It's capital F. This is not finished yet. Now the answer of that is really dependent on what this little f is. And what this little f is just above here. It says probability density of the demand. What's the capital F called? First year probability theory. Does that ring a bell? Yes? No? No? The cumulative distribution function of the demand. Which somehow by definition is exactly this integral. Well, it goes from minus infinity, but in the definition, proper definition, it goes from minus infinity, doesn't it? But above there, but f is only non-zero in positive values, so positive x's. So you can go from 0. And then what's this? Is that correct? Well, okay, so Fs, you have any cumulative distribution function, F is something like that. It's the probability that the appropriate random variable is no more than S. Okay? And that's this integral. You look at all the probabilities that it's below S and add them all together. Addition is infinitesimal, so it's an integral, but addition. And this is where you go from S on. So this integral gives you the probability that the amount, the random variable, is at least S. Okay? And the probability that certain variable is at least S is 1 minus the probability that it's less than S. So you get 1 minus that. Basic probability. So we get this, and now what we want is to get S out of it, but there is no S. So we need to find f of S first, and then from that we'll be able to get S. So what we get is that P plus H times F S plus C minus P equals 0. Is that right? Now we should check that it's really the minimum, not the maximum. But I won't do it. But you have a graph on page 880, which shows how the cost really depends on S. Which you should be able to check if you wanted to. Okay, so now it disappears. Go away. So what have we got? We therefore the optimal order size quantity start the optimal solution has to satisfy that when you look at the cumulative distribution function of the demand in there, so the probability that it's at most how much we order, we want that probability to be what we got from the formula. So P minus C divided by P plus H. Okay, and now the rest is easy. So let's go back to the example. What do we have? C was we still have that one.
So the same as this,
How much do we buy the bicycle for? It's a cheap one, isn't it? £20. It's a child's class. The cost of being short was 45. Said, which was the lost sales, I think, and the cost of having too many was -9, which we got from the £10 salvage value, selling them after Christmas, minus the £1 for storing it over Christmas. Okay, but the cost is actually negative, so it's quite good. And what the demand? Did it say anything about the demand? Okay, so not a lot. So assume that the demand, to stick to what the book says, has exponential distribution with, and the mean demand is 10,000. So what we're looking for how much to order, the optimal order quantity, which needs to satisfy the formula. So Fs is P minus C divided by P plus H. That's our formula. That minimizes the cost, which is 45 minus 20 divided by 45 minus 9, which is 25 divided by 36. Now, this for S star. Now, if it's exponential, do you remember the formula for the cumulative distribution function of the exponential distribution? You have to know that. It's probably in the tables, isn't it? However, it is, I don't know myself, but you have to know that. E to the E minus S star divided by the mean, so divided by 10,000. That's what it is from probability. So when we solve this, we want E to the minus S star divided by 10,000 should be 1 minus 25 over 36, which is about 556 apparently. And this huge thing minus S star divided by this is the one of this 6, which is that apparently.
So what was that called when you did the exponential thing with the distribution function?
What's what called exactly? This or that?
No. It's just when it says d roughly equals the exponential.
Oh no, it's not roughly equals. It has the exponential distribution as a random variable.
And that's how you express the exponential distribution. You need to see
This. Yeah, so the exponential distribution has, if you know the mean, cumulative distribution function is this.
Okay.
That's elementary probability from year one, but I suppose nobody remembers that by now. It's understandable, because there are many other things to remember, but this is what it is. When you check your, I think it's in the tables, in the booklet of tables that you got, it should have all these distribution functions there. So because the demand, we're assuming that demand has the exponential distribution with this mean, that is what the cumulative distribution function is. And because by our theory, it's supposed to be this fraction, which we get is 4.7 roughly. So now we're just looking at this right hand side, this expression over here, trying to solve for S star, and quite successfully, I think, because we almost have it. It has exponentiation in it. We just put the exponentiation on the one side and the rest on the other side, and now you take the logarithm of those both, and the logarithm of this is this, the logarithm of that is that. And so from this, we get the final answer. So 10,000 times 1 point this, so this is 11,856 is what you should order. Which solves the example. So yeah. So you've got everything you need if you want to solve a problem such as the homework problem at the back of the handout, I think. Any questions? Okay, so the key is the formula. That's just disappeared. This one, which you apply. And every time there's going to be a different assumed distribution for the demand. And depending on what that distribution is in the particular case, it's normal or exponential or uniform or something like this. Just plug in the appropriate cumulative distribution function there and solve for the right hand side, which is given by. Okay, so that's how you do homework problem. Any questions? now we're on page 882. So there is read it. Okay, so read it. In this case, we had the assumption that the starting inventory is 0. Okay, so we didn't have anything. Now, assume there is non-zero initial inventory, which is capital I in the book. So let's stick to this. Turns out when you do the analysis in a similar way to what we've just done, which kind of hinted at page 882, I'll just put it here so you can read it. Now what you will get as the answer is very similar. So basically what you're looking at is you've already got something in storage. Now, what you ideally want to have is the same S star, it turns out. Okay? So the optimal policy is going to be the S star you get from the same model is smaller than what you already have. Then you don't order anything if you already have enough, even too much. And if it's larger, then you order the difference. That's kind of the because that formula up there gives you the target inventory size before you start selling things. So how do we summarize it? So the optimal inventory we want to have is the same S star as in the previous model. What you should do is first, if the inventory you have is already how much you want to have or more, order nothing. And if the inventory you have is less than how much you want to have, then you should order the difference. Okay, simple enough. So the explanation why it works is in the book. And finally, there is let's skip this. There's another inventory policy, just quite interesting. Now, there's quite a lot that's quite interesting. I'm too lazy. It's okay. kind of optional stuff. Optional but interesting stuff. Should be running out of time, but we're not. Which is bad, because I have to talk about it. Okay, so one thing is if there is a non-negative, because in the previous model we were assuming that there's no cost of ordering. Okay, so now if there is non-zero cost of placing the order, like we usually had something like that, which is constant and independent of the size of the order. So this is the case. Now, what happens in that case is see page 3. Roughly what well, right there is that the optimal policy is you have two different S's, a small s and a big S. Okay, and your demand is obviously the big S is similar to what we had before. So when you already have more than that, then you don't order anything. If you have less than that, and there is a certain range of the current inventory where the extra money you would gain from ordering up to S star is less than what you would pay for placing the order. Does that make sense? Okay. So, okay. So how does it work? Okay, so we've got, so again, and there is a star, which is what you want to have. So if your inventory is like this, order nothing because you already have enough. Otherwise, if what you have is less than this, then if it's close enough, then you'd have to, if you wanted to order, you'd have to pay a lot, okay, for placing the order, and the amount of money you'd get from the expected amount of money you get from the additional inventory that you would have would not be enough to compensate for the cost you have from placing the order. Okay. So there is a threshold they call little s star in the book. And if I is less than this little s star, then you want to order big S star minus I to get to big S star, which is what you want. And if I is bigger or equal, then this little S star, order nothing, because the expected profit from the extra unit is less than a CW terms. apparently Morrison's implemented an automatic ordering system last year. They blame it for their increased sales over the Christmas period on food items. You see, models like this are quite useful, apparently. Still. Any questions at all? So you've got the homework exercise there, which is quite an important homework exercise. And what else? In the coming 2 weeks now, we'll be looking at airline overbooking and different prices for the same ticket. Very basic models, which of course they're using much more complicated stuff in reality, but we're just starting simple things, give you an impression of what kind of maths is going on there. That's it. Hope